Okay, so here we talk about the magnetic field generated by a straight wire, a long straight wire. Here, it says long, which means infinitely long, 无限长, infinitely long straight wire carrying a current I. So the current doesn't change, it's a constant current. So from the Biot-Savart law, or law of Biot-Savart gives for the magnitude of the magnetic field at the perpendicular distance out from the wire. So we will have this equation. So here we can see mu naught is the constant 4 pi times 10 to minus 7. And then this is the current. We suppose it is a constant. And then 2 pi is of course constant. So for these terms, which is a constant, which means that the B, the magnetic field generated by a long straight wire carrying a current, will be inversely proportional to the distance. Or maybe I can write it as R. Sometimes we use small r, depends. But actually, the R means from this current, we draw a radial line, and then so for this one, the R will be like this, and for this one, the R will be like this. Okay. And here it says if it is semi-infinite. Semi-infinite means it starts from 0 to infinitely far away. So this is from negative infinity to infinity. So for this one is from 0 to infinity, or negative infinity to 0. So it is a semi-infinite straight wire. The magnitude of the magnetic field at the perpendicular distance out from the wire will be half of this. Okay, so yeah. And one thing we consider here is, so here we assume the current is going into the page. So we can use the right-hand rule to determine the direction of the magnetic field. So which is like, if you use a thumb pointing into the page, so you use your thumb pointing into the page, and then your forefinger will be something like in this direction. So your forefinger, and then your thumb have to draw. Don't know how to draw. Okay, so you use your thumb pointing into the page, and then your forefinger will follow the direction of the magnetic field, which means that you can see many concentric circles here, and then the magnetic field at that point will be the tangent line to the magnetic field line. So, for example, for this point, the magnetic field is pointing upward, which is the tangent line to the circle, and for this point, the magnetic field pointing to this side. And of course, the magnitude of the magnetic field is inversely proportional to R, which means that if the point is closer to the current, then the magnetic field will be stronger, and vice versa. Okay, so this is the proof. This is the proof for the equation 29.4 and 29.4 and 29.7. So let's see. We will, of course, use the law of Biot-Savart here, and similar what we have done in chapter 22. Chapter 22, when we try to calculate the E field generated by some discrete structure, then we will just separate the charge into many small segments. Here we also do the same thing, similar thing. So here we have a long, infinitely long wire from negative infinity to positive infinity. We suppose this point is 0, and we concern the B field here, and then with the distance, the perpendicular distance to the wire will be capital R, like this. Okay, so we here will try to separate this current into many small segments like this. So just say if we consider this part, this is ds, and we have a current going from bottom to top. So suppose for this part and for the symmetrical part, ds prime somewhere, if we have s, so we have a ds prime here. So this part will generate a B field, which is also pointing into this point. Yeah, so actually the magnetic field will be also pointing into the page, and the value will be the same. So we can only consider the integral from 0 to infinity, but multiplied by 2. So because this is symmetric to the original point, so we can do some simple simplification here. And here dB is the magnetic field generated by this small segment, and so we can use the Biot-Savart law here. So we just plug it in here. So we have mu0 over 4 pi multiplied by 2. So we only have 2 pi here. And also I is a constant, so we just put it out. And the inner part will be sine of theta times ds, and then r squared. So these two terms will be related to ds, so that we cannot just put them out and then just integrate the 0 to infinity ds, and then it will be infinity. That this is wrong, because theta and r and small r are related to ds. Okay, so let's see how we can do it correctly. So the theta will be the angle between ds and r vector. R vector is from this point to the point we concern. So this is r vector, this is r hat. So we have ds of course pointing from bottom to top, follows the direction of the current. Theta is the angle between them, so this is theta. And actually we can just draw a perpendicular parallel line here. So actually this angle, let's see. So this is 180 degree minus theta. Yeah, right. You're right. So for this one will be 90 degree minus 180 degree minus theta, which will be 90 degree plus something strange here. Let's see, 90 degree, yeah, theta. Oh, sorry, it should be theta minus 90 degree, something like this. Okay, so this is like this, and okay. So here, this is sine of theta. This is sine of this is pi minus theta, and we know due to the identity of the trigonometry function, we know sine of theta equals sine of pi minus theta. So sine of pi minus theta here will be this sine capital R over small r. Small r is the distance from the current to the point we concern. So this is R. So this is capital R over R. Okay, so S will be, and actually we use the Pythagorean theorem. We know that S squared plus capital R squared will be small r squared. So due to the Pythagorean theorem, so we have R equals to square root of this term. So we put it here because we need to integrate it for ds, for the variable s. So we need to change Actually, R is a variable, so that we need to change it to ds and then keep other terms to be constant for the integration. Okay, so here sine of theta will be this term. So we have sine of theta here. Also, r squared will be this term. So we all together have s squared plus capital R squared, the whole term to the 3/2 square, 3/2 power, like this. Okay, so this integration is some variable change, like we need to change s to be capital R times tangent theta, and then ds equals r secant square of theta d theta, and then you plug all this in, and then finally you can find this integration to be like this. And finally, we need to evaluate this term from 0 to infinity. So if we just plug in infinity here, then it will be 1, because we can have this term will be 1 over square root of 1 plus r over s square, like this. If s tends to infinity, then this term will be 0. This term will be 0. So the whole term will be 1. The whole term will be 1. If we evaluate it to be 0, so this 0 plus r squared, so this term will be 0. So this term will be 1. This term will be 1. So finally, we have capital B equals mu naught I over 2 pi r. So far, any questions? So actually, we know that for the infinitely long straight wire with current I, the magnetic field generated by it will be mu naught I over 2 pi r. So we will keep using this result for many times in the following 2 chapters, I think. Yeah, so this is a very important result here. And of course, just according to this part, for semi-infinite straight wire, it will be half of this one. Okay, so next, we consider another case. For this case, we consider the wire is straight. Here, we consider the wire to be a part of a circle, or we can call it a arc, circular arc. 圆弧. Okay. So the magnitude of the magnetic field at the center of a circular arc of radius r and central angle phi in radian. Radian is very important because in calculus, usually the equation will be in radian to keep the formula elegant. Otherwise, if you need to use the degree, then you usually need to divide it by 180 degrees and then multiply by pi. Then the expression will be complicated. Okay, so in radian, so carrying current I is like this. So a little bit different from the previous case. We have a term 4 here, and then we also multiply by 5. So it looks similar, although you don't necessarily need to remember this. And for the if the wire is a whole circle, the magnetic field generated at the center will be like this, mu naught I over 2r. So without the pi. So let's see how we can derive 29.9. So for the total B field, it will be integrating from 0 to 5 dB which means that we try to separate this circular arc into many small segments. And then, yeah, suppose this one is the ds, and this one will be out. This one will be out. So consider you use a forefinger pointing to this side and then cross to out. Then you know that the magnetic field here is pointing out of the page, out of the page. So yeah, like this. So you can use your right hand rule in two different ways. The first way is to follow this one. Your thumb follow the direction of the current, and then your forefinger will be pointing out of the page, which is the same as the direction of this one. Or similarly, you can use your forefinger follow the direction of the current, and then your thumb will be pointing out of the page. Yeah, so it will be the same. Okay, so the derivation here is like we have the Biot-Savart law here, dB equals this term. And then, of course, sine of theta is 1 because for this case, ds is always the tangent line. ds is the tangent line of the circle or the circular arc, which is always perpendicular to the radius. And in this case, this angle is always 90 degrees, which means that sine of 90 degrees is always 1. Okay, so here, I is the constant. R squared is also constant because this is a circle or circular arc. So the distance from this arc to the center point is always capital R. So the whole term is a constant. We need to only integrating 0 to 5 of ds. So and ds is r d phi prime. Okay. So we just substitute the variable. It becomes this one will be r integration of 0 to 5 d phi prime. So which is nothing but r phi. Okay. So integrating 1 from 0 to 5 is nothing but phi. So r phi here. So r and r will be cancelled. We have r and then phi at the top. So the expression is like this. And if it is a full circle, which means that phi equals 2 pi. So here, phi equals 2 pi. So 2 pi and 4 pi will be partly cancelled. We only have 2 here. So we have 2r at the bottom. Okay. So up till now, any questions? Okay. Okay, so here, let's take a look at this sample problem. So it says the wire carrying current I and consists of a circular arc of a radius r and central angle pi over 2 radian, and two straight sections whose extension intersect the center C of the arc. What magnetic field B does the current produce at C? Okay, considering this point. Okay, so this one will be easy. So we can separate this wire into 3 parts. Part 1 is this segment. Part 2 is this segment. Part 3 is the circular arc. So this angle is 90 degrees. Okay, so we can simply imagine that the magnetic field generated by part 1 and part 2 will be 0 because you can simply apply the Biot-Savart law for this segment, ds pointing to this way, and then r is actually this one, which means that the angle between ds and r will be 0 degree. And if we have cross product between ds and r hat, then it will be 0 because sine of 0 degree is 0. Okay, so we don't have magnetic field generated by part 1 and part 2 for point C. Okay, so the remaining part is only part 3. So here, yeah, actually we can write it as a dB1, which is mu 0 over 4 pi times I ds sine of theta over r squared. And this theta is 0, so we have a 0 for B1. And similarly, B2 equals 0. B2 generated by segment 2. And for B3, which is mu 0 I phi over 4 pi r, using the equation 29i. Okay, here we have phi equals pi over 2. So we have a mu naught I pi over 2 4 pi r. Okay, so yeah, pi and pi can be cancelled. So the result will be mu naught I over 8 r. So the total magnetic field generated at point C will be nothing but a B1 plus a B2 plus B3, which is 0 plus this term plus 0, which is nothing but a mu 0 I over 8 r. Okay. And of course, the direction, although it only asks you the magnitude, but actually you can also determine the direction. The direction is nothing but into the page, because you can just follow this run. Your thumb follows the direction of I, and then your forefinger will be pointing into the page. So the direction will be into the page. Or you can use your forefinger, follow this direction, and then your thumb will be pointing into the page. Okay. So okay, so here we have another sample problem. It says two long parallel wire carrying current I1, I2 in opposite direction. What are the magnitude and direction of the net magnetic field at point P? Assume the following values, I1, I2, and D. D is the distance between them. Okay, so here, yeah, here. Let's see. I1 is pointing out of the page. You can see a dot here, and then I2 is pointing into the page. The distance is like this, and then P is this point. Of course, we assume that this is 45 degrees because this is out, this is out, this is 90 degrees. So this is a right angle triangle with equilateral. So this angle is 45 degrees, this is 45 degrees, which means that we can simply have a D equals square root of 2 times capital R, like this. Yeah. Okay, so let's see. So B B1 will be nothing but mu 0 I 1 over 2 pi r using 29.4. Okay, like this. And B2 generated by I2 will be mu naught I2 over 2 pi r, like this. Okay, so here we know r is small d over square root of 2, which is 5.3 over square root of 2, which is 3.75 centimeter. Okay, so next, we can actually find the magnitude. The magnitude will be B1 square plus B2 square, and then take the square root. And why it will be like that? Because we can see here for B1, and actually you can see I1 is here for this, for figure B. Yeah, the I1 is pointing out of the page, and then you can use the right-hand rule to determine that B1 is pointing to the top left with a 45 degree to the negative x-axis. Like this. So use your thumb pointing out of the page, and then at this point, your forefinger will be pointing to the top left. Yeah, something like this. Use your forefinger. Yeah, and then your thumb is pointing out of the page, something like that. And likewise, for the I2, you use your thumb pointing into the page, your forefinger will be pointing to the top right, and also 45 degree with the positive x-axis. So you can clearly see that B1 and B2 are perpendicular to each other. So the total B will be the square sum, and then take the square root of the B1, B2. So we have a B to be like this. Okay, so here we have mu 0 over 2 pi r, and then square root of I1 square plus I2 square. So we can just plug in the value. Mu naught is 4 pi times 10 to minus 7 over 2 pi r is 0.0375, and then square root of I1 is 15a, 15 square plus 32 square. So this is 180 mu t, mu Tesla. Okay, so this is the magnitude of the magnetic field. Okay, so the next is to determine the direction by here. Okay, actually you can try to decompose B1 along x-axis and y-axis, and then decompose B2 in x-axis and y-axis, and then you add them together, and then you try to find the direction. But here we can just simply assume that the coordinate axis is like this. So you can simply find phi here, and then you add it by 45 degree, and which will be the angle from the x-axis to this one. So actually we can do it like phi equals arctangent of. So this is B1. This is B1. So this is B1. B1 over B2 will be tangent phi, which means arctangent of B1 over B2 will be phi. Okay, so it is actually arctangent of I1 over I2, because you can see here B1 over B2. So you can see clearly that mu naught 2 pi r will all cancel. So B1 over B2 is nothing but I1 over I2, like this. Okay, so sorry. So this is nothing but arctangent of 15 over 32, which is 25.1 degree. Okay. So so finally, this angle is theta. Theta will be 5 plus 45 degree, which is 70.1 degree. True x-axis. Okay. So far, any questions? Okay, if no question, let's move on. So here we talk about the force between two parallel currents. In the last chapter, and in the last part of the last chapter, chapter 28, we talk about the other version of the Lorenz force, which is like if we have a current in the magnetic field, then there will be a force like dF equals I. Yeah. So for the Lorenz force, which is like dF, which is Q V. Actually, it should be like F equals Q. Sorry, F equals Q times V cross B. V cross B. So here we will have ds cross B, something like that. So this is the other version of the Lorenz force. So here, if we have two current in parallel, and according to the previous discussion, we know that if we have a straight wire carrying current, then it will generate B field. So if we have another current, just say putting here, then of course this current is in the magnetic field generated by this one, which means that if we have two current in parallel, no matter the direction of the current, then there will be force attracting or repelling them. So actually, the force acting on them will be this expression. So it says here parallel wire parallel wire carrying current in the same direction attract each other, and parallel wire carrying current in opposite direction repel each other. Okay. So, and of course, the magnitude of the force will be this expression. So in the previous chapter, we know the expression will be like that. So in that case, we know. Let's see. For this one, just consider FBA, which means the force acting on the wire B from wire A. So which means that the magnetic field BA is the magnetic field generated by the IA. So BA will be nothing but mu0 IA over 2 pi D. D is the distance between them. Because they are parallel, so you can always define the distance between them. And yeah, and according to this Lorenz force, I will call it Lorenz force. So dF or just F can be written as nothing but I times S cross or L here, L there, L cross B. So L will be L will be this because L is follows the direction of IB. So L has this direction, is in this direction, and then B pointing downward because you use the right hand rule. Your thumb pointing in this direction, and then your forefinger will be pointing downward. So B A like this. So here, if we have just say this one is capital L, this one is capital L, L cross B. So we have L cross B. You use the forefinger pointing in this direction and then cross to BA. Your thumb will be pointing in this direction, FBA, FBA, like this. Okay, so here L, so we have L and B to be perpendicular to each other. So it can be written as FBA equals ILBA, BA like this. And we have BA to be, and of course this one is IB. This one is IB. So we have IB here, and then we have IB times L times this term, mu 0 IA over 2 pi D. So if you just simply simplify it, we have 2 pi D here, and then we have mu naught here, and then IA L times IA IB. So this is the derivation of 29.13. So where D is the wire separation, IA, IB are the current in the wire. So if we have two wires parallel to each other, then we need to have the expression like this to calculate the current attracting or repelling. So you know here we assume IA, IB pointing into the same direction. So FBA will point to this side, which means it is attracting wire B to wire A. And if IB is pointing to the opposite direction, then FAB will pointing to the other side. Because you can simply imagine that L, in this case, L pointing to this side. So L cross BA will be pointing to the opposite side, which is repelling the wire. Okay, here it says the general procedure for finding the force on the current carrying wire is to find the force on the current carrying wire due to the second current carrying wire. First, find the field due to the second wire at the side of the first wire, and then find the force on the first wire due to that field. Yeah, similar to, yeah, so in short, it says parallel current attract each other and anti-parallel current repel each other. Anti-parallel means the wire are in parallel and the direction of the current are in opposite direction. And parallel simply refer to the parallel current and the current is in the same direction. Yeah. Okay, so here come to the most important part of this chapter, which is called the Ampere's law. And as I've mentioned, the Ampere's law is one of the Maxwell equation. So in chapter 23, you have learned the Gauss law, and the Gauss law you need to use the surface integral, and here we need to use another calculus technique called the line integral. And as you can see here, the Ampere's law states like this. The left-hand side is the line integral. The right-hand side is the current. So actually, you can simply compare with the Gauss law, epsilon naught integration, closed integration of E dot dA equals Q enclosed. So there are something similar in the structure. So you can see here is the closed integral. Although this is surface integral, this is line integral. cos 线积分 okay, line integral. And as I mentioned, we have epsilon naught, and then you need to change it to 1 over mu naught. So we move it to the right side. So we have mu naught on the right side. And then here we have a Q. We have Q enclosed. Here we have I enclosed. So they look alike. Yeah, here we also have this circle for the integration, means this is a closed line integral. Here you can see, rather than defining the Gaussian surface, we will define an Amperian loop here. Amperian loop here. Amperian loop simply means the closed loop, which means it is a path, and then it is the loop, which means it begins and ends at the same point. It begins and ends at the same point, which means it is a loop. If it is a path, something like this, this is open, this is open, this is closed, this is closed. Okay. So the line integral in this equation is evaluated around the closed loop called an Amperian loop. So you can see here, this is the line integral B dot ds. So let me simply explain what is B dot ds. Suppose in the space we have some B field. I don't draw too much magnetic field line. Maybe just draw two is enough. And here we have the so-called the Amperian loop. So this is the Amperian loop. Okay. So suppose we need to calculate the closed line integral of a B dot ds. So ds is nothing but we just separate this loop into many segments. So just say this one is ds. And of course, for the loop, we will define the direction. We will define the direction. Suppose in this case it is counterclockwise. This is counterclockwise. So ds will also follow the direction of the loop. And B dot ds is nothing but the inner product. So at this point, we will have B at this point. Let's call it in an coordinate, it is R1. So this is a B of R1. So at this point, we can just calculate B of R1 dot ds. Let's say 1. And then for example, if this one is called dsk, and then this is not straight, but suppose this one is rk. So at this point, we will also have the magnetic field B rk, something like that. So in this case, we can also calculate B rk dot dsk. And then we just add all of this B dot ds together. So this is like the Riemann sum. So this is the line integral. Okay. So here on the left side, we have the line integral, and the right side, it is nothing but a scalar, as a scalar, because we have inner product. After the inner product, it should become a scalar, and then we just add them together. So it should still be a scalar. So it tells you that this is complicated, like the Gauss law. The Gauss law is something like, oh, this is a surface integral. You need to calculate the E dot dA, and then it may take a complicated procedure to calculate, or maybe with some symmetrical structure, then this one may be easy to calculate. And this integral is nothing but the charge enclosed. And here, this line integral might also be difficult to calculate. But with some symmetrical structure, then it might be easy. It might be easy. But this integral is nothing but a constant multiplied by the current enclosed by it. So for this figure, you can see we have I1 pointing out of the page, I2 pointing into the page, I3 pointing out of the page. And if we consider the Amperian loop like this, so this is also counterclockwise. Counterclockwise, which means 逆时钟. And in that case, using the right-hand rule, we know the direction of positive should be out of the page, because you can use the forefinger, following the direction of the loop, and then your thumb will be pointing out of the page. So this is the direction of the positive. Okay, so in this case, I1 is considered to be positive, and it is enclosed by this loop. I2 is negative, and it is enclosed by this loop. So for this Ampere's law, for this loop, if we apply the Ampere's law, I enclosed will be I1 minus I2. I3 is positive, but it is not enclosed by this loop, so we don't count this I3 here. Okay, so here it tells you that I1 is positive. You use the right-hand rule to determine the direction of the integration. Okay, so I1 is positive, I2 is negative, and I3 is not enclosed, so we don't count I3 here. Okay, so yeah, so here we can simply apply the Ampere's law here to get what we have get before, and we have a B equals mu naught I over 2 pi r. And this one, if we use Ampere's law, we can calculate it easily. So here it says we have a wire. It is not thin. It has a radius of capital R. So the radius of this wire is capital R. And we assume the current in this wire is uniform. So if we consider the magnetic field generated by this wire, and then consider the point out of this wire, then the expression is nothing but all the current is lumped in the center point. So actually here for part one, we can simply apply the Gauss law. Not the Gauss law, the Ampere's law equals mu naught I enclosed. So for this one, B is pointing in this side because I is pointing out of the page, and then you use the right-hand rule. Your thumb pointing out of the page, your forefinger will be in this direction. So at this point, B pointing to the top right, and then ds also point to the top right. So B dot ds, the theta between B and ds will be 0. So B dot ds is nothing but BDS. And BDS, we also assume that B is uniform over the whole circle because the distance are the same from the center to the point on this loop. So in this case, we have nothing but 2 pi r times B, because B is a constant. So it is nothing but B integration of ds. ds is the circumference of the circle, which is 2 pi r. So we have 2 pi r times b, 2 pi r times b. Okay. So yeah, that is. So on the right side, it is nothing but mu0 and I. I is the total current in this wire, total current in this wire. So in this case, we will have B equals mu0 I over 2 pi r. And for part two here, we consider another case. We consider the Amperian loop to be somewhere here. Somewhere here. Or maybe I can, maybe, I'm not sure. Yeah. So here we consider the Amperian loop like this. Okay. So similarly, for the Ampere's law like this, mu naught I enclosed, this sign is nothing but 2 pi r times b. However, at this time, I enclosed is not all the I, because some of the I, part of the I are outside of this loop, so we don't consider that part. And of course, here we consider the current density is uniform over the whole wire, which means that we can have equals mu0 I enclosed. So here, I enclose over 4 pi r square, which is the cross section area of this one. So I enclose over this one will be the current density in for the inner part, and which is of course the same as the current density of the whole wire, which is I over pi capital R square. So this is J for the inner part equals the J for the whole part. Okay, so pi and pi can be cancelled. We will have I enclosed equals I times small r square over capital R square. Okay, so we can just use this one plotting back into here. So we have 2 pi r b equals mu naught I times R square over capital R square. So finally, we will have B equals. Here we can cancel this R with this R. So finally, we will have mu0 I, which is this term, and then we still have R here, so we have R here, and then over 2 pi R square, which is this one. Okay, up till now, any questions? If we have no question, let's have a 10 minutes break.